Welcome back to the Datarekha audio guide. I'm Diya.
And I'm Arjun. Let me start with a horror story. A team fine-tunes a model on a big data center GPU, ships it to a partner running a normal gaming card, and the moment the partner hits load, the process crashes instantly. No error in the code. The model simply does not fit in the memory.
Okay, so this is the wall everyone hits the first time they try to run a real model on their own hardware. What's the actual mismatch? Why won't it fit?
It's pure arithmetic, and the beauty is you can do it in your head. Every weight in a neural network is a number, and the question is, how many bits you spend storing each one? The default training format is FP32, 32 bits, 4 bytes per weight. So the memory is just number of parameters times bytes per parameter. For a 7 billion parameter model in FP32, that's 7 billion times 4, 28 gigabytes.
And a typical consumer card has what? 24. So a 28 gig model against a 24 gig card. It's over before it starts by a hair.
By a cruel little margin. Yes. So the fix is quantization. Store each weight in fewer bits. Drop to FP16, half precision, 2 bytes. Now it's 14 gigs. INT8, 1 byte. 7 gigs. INT4, 4 bit, half a byte each. 3.5 gigs.
So going from FP32 down to INT4 is an 8-fold cut in memory. The model that needed a $10,000 data center card now runs on a $500 one.
That's the entire economic unlock in one sentence. 8x smaller, and a whole class of hardware opens up. But the obvious worry is, surely you can't just throw away that many bits for free. Something has to give.
Right, that's exactly where I get nervous. You're rounding off most of the precision in every single number. Why doesn't the model just fall apart?
Beautiful question. And the answer is subtle. It works because weights are static. Computed once during training, then frozen. They represent smooth, slowly varying learned features. When you round them, you introduce tiny errors. But those errors are spread across billions of values, and they largely cancel out. The damage averages away.
You said weight specifically. That sounds like a deliberate contrast. As if there's something you can't quantize the same way.
Sharp catch. There is activations. Those are the intermediate results computed fresh on every forward pass. And unlike the frozen weights, they can spike two huge values unpredictably depending on the input. Quantize those aggressively, and you get visible quality drops. So most schemes quantize only the weights and keep the activations in FP16 at runtime.
Now hold on, that raises something. If the activations are running in FP16 but the weights are stored in 4 bits, how do those two even multiply together? Is the math happening in 4-bit?
And this is the single biggest misconception about the whole topic. INT4 does not mean 4-bit math everywhere. The weights are stored in 4 bits to save memory. But right before the matrix multiply, the GPU dequantizes them back up to FP16. The arithmetic happens in 16-bit. You are saving memory and bandwidth, not doing low-precision compute.
So then where does the speed up come from? If the actual multiplication is the same precision as before, you'd think same math means same speed.
Because on modern hardware, the bottleneck isn't the compute. It's loading the weights out of memory in the first place. The chip spends most of its time waiting on data to arrive. Shrink the weights to a quarter the size, and they stream in 4 times faster. So throughput improves even though the math is identical. The memory was the traffic jam, not the engine.
Okay, so how do I actually do this? Because I keep seeing these 4 names thrown around: GPTQ, AWQ, GGUF, bits and bytes. And I genuinely can't tell when to reach for which.
Here's the map. GPTQ was the first to bring NT4 to LLMs without quality collapsing. It quantizes layer by layer using a small calibration set to minimize the error at each step. Solid on any GPU. AWQ is the clever evolution, activation aware. It spots which weights get multiplied by large activations, the salient ones, and protects those from aggressive rounding. Often matches or beats GPTQ with simpler calibration.
Those both sound GPU flavored. What if I have no GPU at all?
Then GGUF is your format. It's what llama-cpp and Ollama use. It offers a family of levels like Q4KM, and that KM suffix is smart. It mixes bitwidths across layer types, spending more bits on the sensitive layers. And crucially, GGUF runs on CPU. That's the one for a Raspberry Pi with no graphics card. Bits and bytes is the convenience option. It quantizes on the fly in Python as you load the original checkpoint. No offline step. Great for experiments, but it needs a CUDA GPU.
Let me make sure I land the trade-off because that's what I'd actually need to decide. What does this cost me in accuracy?
INT8 is almost always free. Across the Llama, Mistral, Quen families, you lose under 1 point on standard benchmarks. Indistinguishable from full precision for most production. INT4 costs more, typically 2 to 5 points on reasoning and knowledge tests. And below INT4, 3-bit, 2-bit, quality falls off a cliff. Don't go there for general use.
Here's the insight I want to test then. If a big model handles INT4 better than a small one, does that mean I'm sometimes better off running a huge model squeezed into 4 bits than a small model at full precision for the same memory budget?
That is exactly the punchline, and you got there yourself. Larger models tolerate INT4 far better than small ones. A 70 billion model quantized to INT4 often beats a 7 billion model in full FP16. Better quality and more memory efficient at the same time. So the right question is rarely, how do I shrink my small model? It's what's the biggest model I can quantize into the memory I've got.
One sentence to take away?
Quantization stores weights in fewer bits, not your math in fewer bits. And the smart play is fitting the largest possible model into your hardware, not running a small one full precision.
Shrink the storage, keep the engine. That's the Datarekha audio guide. See you in the next one.